So the stress strain curve is the graphical representation of the relationship between stress on the y-axis and strain on the x-axis of a material that's loaded to failure. Stress is the force per unit area, and that's measured in newtons per meter squared. Strain is the change in length of material relative to the original length, and that doesn't have any units. The curve itself is divided into two parts. You've got the elastic zone, which is the first part, and then you have the plastic zone. In the elastic zone, as you stress the material, the changing length is proportional, and that follows Hooke's law of proportionality. The slope of the curve indicates the stiffness of the material, and that's measured by Young's modulus. The steeper the curve, the stiffer the material. In the elastic zone, any deformity that does occur is completely reversible when the load is removed, and that's the definition of elastic deformity. When you reach the end of the elastic zone, you reach the limit of proportionality, or the yield point, and beyond that you then enter the plastic zone, and any deformation that happens here is non-reversible. As the material continues to be stressed in the plastic zone, it continues to change length and reaches a point where you have strain hardening. Here the stress needs to go up significantly for any further strain in the material until you reach the ultimate tensile stress, which is the highest point in the curve, and that represents the strength of the material. Beyond that is the region of necking, where you have a sudden decrease in stress and a sudden increase of strain in the material as the cross-sectional area reduces just before the material fails here. So if the load was to be removed at this point, the material will then return back to the baseline parallel to the curve in the elastic zone. So the difference between this point and this point represents the permanent deformation of the material. Now, toughness is the amount of energy that a material can absorb before fracture, and that can be calculated by the area under the entire curve. The stiffest material that we use in orthopedics is ceramic, and that has the steepest curve. This is then followed by cobalt chrome, stainless steel, titanium, and then cortical bone. Following on from that, in terms of decreasing stiffness, you have cement, so PMMA, polyethylene, cancellous bone, and then tendons and cartilage.